Welcome back to ECE 441A, 541A. By way of announcement, homework number 3 is due on Wednesday of this week. And if you were not successful uploading your lab onto D2L over the weekend or on Friday evening in particular, I think people were more successful over the weekend. Don't worry so much about getting it in after the deadline. That I will accept. Just put it there if you haven't turned it in, either physical hard copy or through D2L. I need to see where we're at with lab number 1. Today what I want to go over are just a few comments on homework number 3. Hopefully that will minimize the time that you sit scratching your head wondering what's going on. Then we will simply illustrate that, or the connection between the poles of a transfer function and the eigenvalues of the system matrix. I want us to start really appreciating that connection, because that's really lab number 2. We will be playing with the dynamics of your mass spring damper system and seeing what we can do with chapter 4 material, which is feedback, and chapter 5 material, which is performance. So we're getting into chapters 4 and 5 with the new material. Homework number 3, there's several problems, but there's several assigned problems. Maybe there are some issues with those problems, or some comments that I can make that will hopefully minimize your uncertainty. There is basically a typo in problem 320 with respect to the curve. Don't worry so much about that. I think the relative shapes of those are okay, and you can sort of see the behavior that you want to see with respect to decaying exponentials. And where those start are okay if you don't sort of pay attention to one of the labels on the iodine curve. I think they needed to divide by 10 to the 16th instead of 10 to the 15th, but if you overlook that, then you should be okay. On problem 24 in chapter 3, you're given a system that has 2 inputs and then it has a disturbance, and we can treat disturbances in the same way that we can think of inputs. They may not be coming in the same direction or with the same B matrix column, but you can treat it as an additional input into your system, as illustrated here. You may be given the dynamics x1 prime and x2 prime, and you can see that x1 prime and x2 prime depend on input 1, input 2, and a disturbance D. But if you sort of put on some filters on your glasses and say, let me just consider that D to be a U sub 3, it looks just like another input. And if you treat it that way, you could collect those into 3 columns, and now your input matrix is 2 tall and 3 wide. It's a 2 by 3 matrix. But they give you that these inputs are actually constants, and you can see then that x1 prime is driven by 1 and x2 prime is driven by 2. And you could sort of put those in and now say, oh, just let me excite this system with a step. You really just have 1 input, with the column, B column, being 1 and 2, with a constant input of 1. Is another way of sort of thinking about that if you want to simplify that or enhance your understanding of what's going on in that particular situation. But that collapsing of the 3 columns into 1 is really because the structure of those inputs, U sub 2 and D, are both constant. They look the same. Now, if the disturbance was a sinusoidal disturbance, and the input was a constant, you couldn't be combining them in the way that we are combining them. You would have to treat those as separate quantities. Finally, I'm hoping you pay a little bit of attention to how these problems are stated in terms of this is CP 3.4. That means it's a computer problem, which means they are expecting you to be using MATLAB. And if you look at sections 9 and 10 in Chapter 3, that should help you with the commands that you need to execute CP 3.4. The way that I would prefer that you turn this in is I want you to be able to understand your material in the future when you look at it. Meaning if you simply turn in your answer, that may not be enough. You may want to turn in what you could look at in the future, maybe the script, maybe the commands, maybe you just save it as a diary file, but you now can see what commands you issued in order to produce the output results that you're getting. And the figures, if you have to sketch something, well, plot something in MATLAB, it's nice to have those figures also. So I would suggest that in a MATLAB type of problem, you could even have some handwritten notes to get you going as far as thinking through what you're doing. Include those, include your MATLAB commands, either in a script or a diary file. Include your results, whatever those might be, either as numbers or as plots or figures. Does that help on the MATLAB piece or the CP 3.4? CP3, was that something, was there a CP something somewhere in a movie? CP3PO, something like. Anyway, that's not what this is. This is a computer problem 3.4. I don't know, I kept saying CP and I'm going, I think I've heard that somewhere before. All right, let's now talk about this connection between transfer functions. Transfer functions are a way of modeling the system in the frequency domain, and the state space representation is a way to model the system in the time domain. And obviously, if it's the same system, those models or those representations better be consistent. One way that you can see the connection is that the poles, those things in the denominator of your transfer function, let's just concentrate on a single input, single output system, the poles or the roots of your denominator polynomial, those poles can actually be shown to be the same as the eigenvalues of your system matrix. Here we're assuming that we haven't introduced any feedback yet. But our system is given by these three matrices. That's for what kind of a system? That was a vague question, but now I'm wanting the word proper to be in your description of this system. What kind of a system is x prime equal ax plus bu, y is equal to cx? It's strictly proper because we do not have that direct feed-through term, that D, the D matrix in the output equation is actually 0. We do not have a direct feed-through matrix in our representation here, and because of that we have a strictly proper transfer function, which if we get into the transfer function, what does that mean? A strictly proper transfer function. It means we don't have a direct connection between the input and the output, which if we translate that into something about the polynomials in the numerator and denominator, what does that mean? So the numerator polynomial, in terms of its order, is strictly less than the degree of the denominator polynomial. And that means we don't have this direct connection if I'm drawing my arm with my arms, but you now can hopefully start to visualize these block diagrams, and you do not have a direct path from your input to the output. It has to be filtered through some integration operations to get eventually to influencing the output. That's a strictly proper system. With these two representations, remember how to compute a matrix inverse. The inverse of a matrix is 1 over the determinant times the adjoint of that matrix, and that's this, you start eliminating rows and columns, and then you find the cofactor of the resulting submatrix, and then you transpose that. That's this adjoint matrix. That's a matrix, and it's going to be square. But what's in the denominator of that inverse is this determinant of Si minus A. If we compare this determinant of Si minus A with what you've maybe seen in a math class, there might be a connection. There is a connection. You should, in a math class, well, not every math class, but let's say a linear algebra type class, you might be learning about eigenvalues and eigenvectors. Here, this definition of the matrix inverse, this is a symbolic matrix inverse. Remember, we did that with our calculator Friday. We could quickly do that if we just introduce some variables s or x on our calculator and raise it to the -1 power. We can now have this poles of our transfer function being the roots of the determinant, being the eigenvalues of our system matrix. And what is the definition of an eigenvalue? Those are the values of S that satisfy what expression? Okay, so you might have seen this as lambda I minus A equals 0, right? We are now simply going to make the connection a little bit more direct and just say that variable, that constant, which can be complex, that's now this S. It's our complex frequency variable, values of S that satisfy, and I'm using some notation here, these vertical bars mean that we're dealing with the determinant, and this particular expression, that determinant set equal to 0, you will see that, or we might refer to that as the characteristic equation. And that's our connection with the time domain representation of our system. X prime equal AX plus BU, Y is equal to CX. The dynamics of that system are contained in the eigenvalues of the system matrix A. If you want to know how is this system going to behave if you walk up and kick it or give it a bump, it naturally will shake or move based on the eigenvalues of your system matrix. Just like you're used to thinking about the poles of the transfer function influencing the dynamic behavior of your system. Again, you can invoke your calculator. I'm assuming that everybody went home this weekend and started talking to your parents about calculators. And what did we do last time? Oh yeah, we were saying old school. What were we having calculated old school? The inverse of a matrix? Is that what your mom was helping you with this weekend? Inverting your matrices. Here you can actually invoke the eigenvalue. There's even an eigenvector command, but if we remember the matrix that we were dealing with before, we had in our example, A was minus 3, 1, minus 2, 0. We could put that into our calculator with a square bracket of minus 3, comma 1, semicolon, minus 2, comma 0. The semicolon says start a new row. And I did that before class because I was not very good at it in real time, so I just went ahead and typed it in before I converted my laptop into a tablet and had to do it with a stylus. Here is eigenvalue of that matrix, and you could find the eigenvalue if you just go look in your dictionary of functions, and it's right there. And now I just hit enter, and then you have to remember to find the square bracket, and then it's not that big of a deal if you can get the right numbers. The hard part is finding all of these special characters or a semicolon. What did I do? Not do the... Where's my 2? Told you, didn't want to do it in real time. And that's now how you can find the eigenvalues of a matrix rather easily with your calculator. Or if you were doing it old school, your parents were doing it this weekend, I guess, finding the... And here I'm using lambda. Lambda I minus A, that determinant equal to 0, says that we now take this lambda on the diagonal and subtract the A matrix. To find the determinant, that's not that difficult. We simply multiply the diagonal terms and subtract the product of the off-diagonal terms. We now realize that that's lambda squared plus 3 lambda plus 2 equaling 0. That factors nicely, and now that gives us these eigenvalues at minus 1 and minus 2. And maybe I should say it gives us one eigenvalue at minus 1 and a second eigenvalue at minus 2. The nice thing about that is that now tells us how our system will shake or move when we excite it, or that provides us with these modes. What do I mean by modes? Now the modes are influenced by the poles, and those poles, those eigenvalues now are exponents in these, they are the terms in the exponents of our modes, so that we now have e to the minus 1 times t and e to the minus 2 times t. Those are the modes, and that's how our system would naturally like to evolve. And if our system matrix has complex eigenvalues, then what happens? Pardon? Our system has some oscillation. It depends on where those complex poles or eigenvalues are located. If they're right on the imaginary axis, it just sits there and shakes forever, doesn't it? It's an oscillator. It doesn't have any real part. If the poles are in the left half, they have some exponential decay to those oscillations, and that's then going to give you the shape or the modes of your system response. Which in your homework problems, you are looking at some of these initial condition responses. You're exciting your system by putting variables at some initial value and seeing how they decay with time. And they decay based on these exponential decay concepts. Questions on that? That's chapter 3. We're done with chapter 3. If you're reading along, hopefully this weekend you started reading chapter 4 in anticipation of where we were going. Let's get into chapter 4. which is dealing with feedback. Here is a very standard block diagram from a controls perspective, but what we will be looking at may not just be the transfer function between the reference signal R and the output Y. We actually might be interested in other transfer functions. And in particular, the transfer function may be between the reference signal R and this signal coming out of the summing junction, which we many times will label with an E, which could be a pseudo error. If H was 1, then E would be like this error, the difference between the reference and the output. E now is the difference between the reference and a filtered version, H of SY, of the output. So we're comparing the reference that we put in with a filtered version of our output Y. And we may actually make G, we may put more things into G. What we've been doing so far is simply modeling systems. Now what we want to do is start designing systems. We want to start putting our own blocks into this block diagram configuration to improve or make our system behave more the way that we want it to behave. Now, what's the transfer function between the reference input R and the signal E? Is it 1? Looks like it just goes right in there, doesn't it? But we have dynamics and we have feedback, and so the transfer function between R and E is not as simple as just 1. And now let's find what that transfer function is. We can say that E is, in fact, R of S, the reference signal, minus HY, but let's just keep going. Y is GE, because it brings good things to life. Sorry. But we have to have fun, right? It's a Monday morning. So now we have R is, what did I just say, minus G of S, H of S, E of S. Is everybody clear on where that came from? And we are adding and subtracting signals. We have a signal E, we have a signal R, and we have a filtered version of E. E is filtered through the plant and this feedback path H, which might be a controller, it might be sensor dynamics, and G may actually be a collection of our system and a controller. We may, if we dig into it, it may be more involved than just that one transfer function. This we should be comfortable with. We can now combine the terms that are similar, which means let's pull the E's to the left and factor out everything that's not E on the left-hand side. We are assuming single input, single output, so we can divide that transfer function to obtain our expression for the air signal, or this E signal, is now 1 over 1 plus G of S, H of S. This expression then in the square bracket is, in fact, our transfer function between the reference input And I'm going to go ahead and just say, and the error signal. And that may be a transfer function that we are interested in. We may want that error signal to go to 0 for various reference input signals, R of S. And we may be interested in this transfer function in contrast to, do you remember what the transfer function is between the reference signal R and the output Y? You could find it now quite easily because we know that Y is GE. And we would just then multiply this right-hand side by G, and that would give us the transfer function times the reference signal. Or we now have G over 1 plus GH is the transfer function between the reference signal R and the output Y. There are two different transfer functions, all from the same system. We have G over 1 plus GH, we have 1 over 1 plus GH. And we may be interested in both of those in understanding or designing or building certain properties into our system. What can we do by introducing feedback? What is something that you use feedback for every day? Of course, that's what I use every day. Did everyone hear that? Eliminate steady state error. And you're trying to eliminate that steady state error on exams, aren't you? Your target, your reference input is 100, and you're trying to minimize the difference between your score and the ideal reference of 100. Right? You're trying to drive that error to 0. In the steady state, by the time you hit the final exam, you want that error to be a minimum. If it wasn't a minimum now, or if it was, you don't want it to grow. Right? So, that was my third characteristic property of a feedback, to reduce. That I guess that's what you guys are thinking about all the time, is reducing steady state error. Meaning, you have a thermostat in your home. You hope your AC or heating system works properly so that you can reduce the air between your reference temperature and the temperature in the environment. That's a controls problem. And you're trying to reduce the steady state error with feedback. You measure the ambient temperature, and then you control your heating or cooling device appropriately, depending on what the difference is between the reference temperature and the ambient temperature. What about, I was thinking more about a bicycle and feedback, or a car and feedback. If there was no feedback, you would be all over the road, right? You just instinctively apply feedback when you're steering your car or when you're riding your bicycle. The bicycle is an inverted pendulum, and you can quite naturally, with some practice, control that. What was your system doing in the lab? How did your system behave in the lab? Did it have any overshoot? Yes. Was it acceptable overshoot? It depends. That's usually an appropriate answer, isn't it? It depends. It depends, one, on your system. Some people didn't have much overshoot. Some people had others. What were some of your percent overshoots that you measured? 40-something%, 60%, pretty high percent. Where were your polls? So maybe you don't remember their numerical value, but were they not very far into the left half plane, but pretty high away from the real axis? Maybe like -1.5 up to 17 for the imaginary part. So they weren't at an angle of 45 degrees, were they? They didn't have the same real part as imaginary part. That would be this theta angle of 45 degrees. They had a much bigger angle, didn't they? Because they weren't very far into the left half plane before they went skyrocketing up into their imaginary component. In lab number 2, we are actually going to try to change that. We want to use feedback to improve the stability. Now we want to make that angle maybe smaller. Naturally, the system may want to have a huge angle. We want to change it. And we're going to change it not by mechanically changing the system. We are going to measure position and velocity and feed those signals back electrically to change the dynamic behavior of our system. With feedback, we can improve stability. My third property, I guess it's not on the tip of your tongue, we can use feedback to reduce sensitivity. We're engineers, maybe we haven't had a lot of sensitivity training. No, we're good with sensitivity, especially in this environment, right? So now let's learn a little bit more about sensitivity and what that means. So let me try to explain what we're talking about with respect to sensitivity. Because I think we have a pretty good understanding of the first two properties that we can use feedback to enhance or allow us to improve upon. To think about sensitivity, suppose we have a system, and suppose there is uncertainty. And let's say system parameter values. As an example, or for instance, the winding resistance, all of that wire in a motor, when you start operating that motor gets hot, doesn't it? There's a lot of I²R losses, and the winding resistance has a part in that, or plays a part in that. The winding resistance of an electric motor can actually change due to temperature, for example. An electric motor changes as the temperature of the motor rises. Let's say you're now commanding this motor to operate, and it's been operating for a while, and now the winding resistance has changed because the motor's getting hot. You're going, oh man, I wanted to stay on the road, or effectively I wanted that motor to behave the same as when I started it up, or have similar properties now and an hour into the future after that motor has been working for a while. That's why we want to use control. A good control system should maintain satisfactory performance in the face of parameter uncertainties. Or think of variations in your system. Let's now, so that's the idea behind it. You may have a system and it might be changing with time. Maybe it's aging, but you want that system to behave the same this week as it might in 4 weeks. And with control and with feedback, you can improve upon that system's ability to behave in the face of parameter uncertainty. Here's sensitivity. Suppose the system, I guess I should be writing with green because now I'm talking about the plant. The plant is our system. Let's say that's G of S. And let's say that that plant changes by some amount. We'll call that delta G of S. We have a motor, and it's in this big system. Now the motor changes for whatever reason. It now has a change, and we're labeling that as a delta G. We want to know, how does the overall system transfer function change as a result of that change in our system? How does the transfer function change in response to our plant change? Or we're asking, what is delta T of S? To do this, to really be consistent in analyzing changes, we really want to look at relative changes. Let's now examine relative changes in our plant and what those then result in relative changes in our transfer function. Meaning, here's the change in our transfer function, but we want that to be relative to the transfer function itself. So let's then normalize that by the transfer function t. And we want to see, how is that ratio relative to the relative change in our plant itself. This is now our quantity that we're interested in. We have a delta T over T divided by delta G over G. And you didn't take 2 or 3 semesters of calculus to just not use it, right? So delta means a big change, but in calculus we like to think of differential changes. And differential changes allows us to start taking derivatives. So now let's look at this in a differential setting where the deltas become smaller, infinitesimal changes, these sort of small variations. So let's now say in a differential setting, i.e., that is, let's let delta G go to del G and delta T to del T. In a differential setting, if we let delta G be del G and delta T be del T, this ratio that we just identified up above is actually called the sensitivity of the transfer function, which we're labeling as T of S, to changes in the plant, which we are labeling as G of S. And we like to use notation, so now the sensitivity, that ratio of changes, relative changes of transfer function and plant, we will label with S for sensitivity, but now we say that's the sensitivity of our transfer function, so we give it a superscript. With respect to changes in the plant, we give it a subscript G. That's our notation for the sensitivity of the plant, or I'm sorry, the transfer function to changes in the plant. Meaning we now are defining S sub T of G to be the partial of T over the partial of G over G. But if we clean up the G and the T, those are transfer functions. The G's in the denominator of the denominator, which really gives it upstairs in the numerator. And the T is in the denominator of the numerator, which says that it's effectively in the denominator. Now, if we take the partial of the transfer function with respect to G and scale it by G over T, that will give us the sensitivity of T with respect to G. Now, we can even make that even more interesting by remembering a little calculus. If we now take the derivative with respect to x of the natural log of f of x, what does that look like? Do you remember your calculus and derivatives? What happens when you differentiate the natural log of a function? Okay, the fx goes downstairs, doesn't it? We have 1 over f of x times df dx. Meaning, if we now use that in our sensitivity expression, we can also write s sub t, or s sup t sub g is the partial of ln of t over the partial of ln of g. And because of the ln, we now have the t over g or the g over t coming out immediately out in front. That now allows us to take into account the relative changes in these transfer function relative to the system. Let's look at some cases. Let's compare sensitivities, and the first one is maybe a straightforward one. Let's now comparing sensitivities. Let's do it with open loop versus closed loop transfer functions. So now we have closed loop transfer functions and open loop transfer functions, and we want to see how do their sensitivities compare. Here's the easy one. Let's look at the open loop case. If we have an open loop system, what we mean by that is there is no externally applied feedback. What is our transfer function between the input R and the output Y. What is T open loop of S? G of S. It's open loop. So T sub 0 of S is just the plant itself, G of S. If we now compute the sensitivity of the open loop transfer function with respect to G, that's now this partial of T naught with respect to over T naught over partial of G over G. Or that's G over T naught, partial of T naught with respect to G. But we can now compute that partial of T naught with respect to G. If we treat T naught, that's our open loop transfer function, what is that expression? This partial of T naught with respect to G. T naught, we said, was just G. And what's the partial of G with respect to G? 1. So that now we can compute the sensitivity of the open loop transfer function with respect to G. That's now this G over T naught, but T naught was G, times partial of T naught with respect to G, which was just 1, and there's our sensitivity. And does that make sense? If we have a change in our plant, that same change is going to be seen in the transfer function for an open loop system, because it is the same thing. So if we had a 10% change in our plant, we would see a 10% change in our open loop transfer function. Let's now compare that with the closed loop. Our closed loop is this system that we've been playing with. Let's say it's G in the forward path and H in the feedback path. The transfer function for the closed loop system, T sub C of S, is this G over 1 plus GH. We've derived that before. And now let's compute the sensitivity of T sub C with respect to G. That's now the partial of T sub C over T sub C over the partial of G over G. Or this is now G over T sub C, partial of T sub C with respect to G. Now we need to find this partial. The partial of T sub C with respect to G is now the partial with respect to G of G over 1 plus GH. And this is why you took the calculus, to remember the quotient rule of differentiation. Because G is appearing in both places, numerator and denominator, and we're taking the derivative with respect to it, which allows us now to say we have the denominator times the derivative of the numerator, partial of G with respect to G, 1, minus the numerator times the partial of the denominator with respect to G. What's that? 1 plus GH differentiated with respect to G. That's just H. All over the denominator squared. Well, if we look at this GH there gets canceled by that GH, and we're left with this being 1 over 1 plus GH quantity squared. But that's this piece right here in square brackets. We now need to scale that by G over T sub C to obtain the sensitivity. Doing that, the sensitivity of T sub C with respect to G is now G over T sub C, partial of t sub c over g, with respect to g. Now I have g over 1 plus gh times 1 over 1 plus gh squared. If we do some canceling, that g cancels that g. This is one of those, so that cancels one of those, and the sensitivity closed loops of the closed loop transfer function with respect to the plant is 1 over 1 plus gh. And how does that compare with the open loop? The open loop was 1. A change in the plant directly influenced the transfer function. Now, if our plant or feedback is big gain in our system, the sensitivity is going to be smaller, isn't it? It's now reduced. And that's a good thing. That's what feedback has allowed us to do. We'll pick up with more examples on sensitivity on Wednesday.